Okay, so we're going to talk about synchronous counters today, specifically SSI logic, or small scale integration. And hopefully you know from previous lessons that we've done, that means that it's incorporated with flip-flops. And they are simultaneously, oops, I can't spell SI, simultaneously clocked. So you'll remember from asynchronous that there was what we called a ripple effect, because one clock would feed into the next, and that caused a slight delay between flip-flops, so you get a ripple effect. Well, since we're simultaneously clocking our flip-flops, there is no ripple effect, so that's one of the advantages of synchronous counters. The disadvantage is that it requires more logic in order to make it work. Okay, so you should have a copy of this insert to put in your notebook. So we're going to create a 3-bit up counter with these flip-flops that are simultaneously clocked. So that's what it means to be a synchronous counter. So what that means is that our clock is actually connected to each one of the clocks for each one of the flip-flops. Okay, so let's go back and remember what it means to count up. So we're going to call this one Q0, Q1, and Q2. So Q0 is going to be our least significant bit. Then we have Q1, and then we have Q2. Now remember, when we count, we're going to have 8 rows because we have 3 bits. So the first bit, the least significant bit, is just going to alternate. The second bit is at half that frequency. And then the third bit is at half of that frequency. That's how we count in binary. And because a flip-flop is a frequency divider, it divides the output is half of the frequency of the input. It's a natural counter. So we're going to use that, just like we did for the asynchronous counters, to create our up counting clock with these flip-flops. So let's remember that we're going to have our clock input. So our clock input is going to look like this. It's going to be doing a regular frequency rise and fall. Q0 is going to be the output of the flip-flop. So our clock will go to the input. That's the input of our first flip-flop. The output should look like this. So we're going to notice that our clocks are falling edge triggers. So we're going to be changing Q0, the output will be changing on the falling edge, which is right here. So our Q0 starts at 0. When it sees a rising or a falling edge, it will go to 1. At the next falling edge, we'll drop back to 0. Falling edge will rise to 1, etc., etc. So what we end up with is our 0, 1, 0, 1, 0, 1. So that's where we get our first clock output. Now keep in mind we want our output to toggle. So just as a little reminder, our JK flip-flops work like this. Let's see, I gotta find a place to put this. So I have J, K, and Q0. So when I have a 0, 0, the possibilities are 0, 0, 0, 1, 1, 0, and 1, 1. Now, when I want my flip-flop to toggle, I want both of my inputs to the JK flip-flop to be set to a 1. So what that means is I need both of those set to 5 volts. Okay, so we've created the first part of our counter. So that first flip-flop will be creating a Q0 output that will be alternating 0, 1, 0, 1, 0, 1 at half the frequency of the clock input. Okay, so now we're going to go to Q1. Now let's look at what we want Q1 to do. Okay, Q1 we want it to be at half the frequency of Q0. So I want it to register 0, 0, 1, 1, 0, 0. So the output should look like this. Rise to 1, fall to 0, etc. Now remember that we've already connected it to the clock. So without any other logic, every time I have a falling edge, I should have a change here. Falling edge would be a change here, but notice it only changes every other falling edge. Here was a falling edge, no change. Next falling edge is when I change. So there has to be some additional logic. I can't just let it alternate on this clock or the output will look just like Q0. So what is the condition that I need to have? Well, notice on this falling edge, when Q1 does not change, Q0 is at 0. But on the next falling edge, when Q1 does change, Q0 is at a 1. So what I want is, I want the change in Q1 to happen at the clock and when Q0 is equal to 1. So I've already got the clock input going, so how am I going to create a no change here and a change there? Well, remember on our JK flip-flops, when we have both J and K set to 0, there's no change for Q. So that's what I want to have happen. So if I can send a 0 to JK here and a 1 to JK here, it will toggle where I want it to toggle. So what I'm looking for is Q0 to be 1. Over here, Q0 will be 0. So if I take the Q0 output and connect that to my J and K, that will allow this flip-flop to toggle only when the clock has a falling edge and Q0 is 1. So that's what's going to produce the output for Q1. So go back and review that if you're still confused. Remember, we're looking for the clock input, which we've already attached, and Q0 to be at 1. So when Q0 is at 1, J and K are at 1, and my Q1 will toggle. But when Q0 is 0, my JK will stay the same no matter what the clock is doing. Alright, moving on. Q2. For Q2, I want half the frequency of Q1. So I'm going to have 0, 0, 0, 0, and then a toggle to 1. So it should look like this. So here, I have the clock input, but I also need other conditions to make sure that it doesn't toggle here at this location, and it doesn't toggle at this location, but it waits for this location. So notice that the condition for this Q2 to toggle is a falling edge, and Q0 is 1, and Q1 is 1. Okay, so even here, where Q0 is at a 1, my Q1 is still at a 0, so I don't get a toggle. Over here, I've got Q0 at 0, but Q1 at 1, I still don't want to toggle on that falling edge. I want to wait until I have a falling edge where both my Q0 and my Q1 are 1, then I can toggle my Q2. So I've got to connect a little more logic to my J and K. So I'm going to use an AND gate to do that. Coming back down to here. I need an AND gate with outputs to both J and K, The condition being that Q0 and Q1 are both 1. Otherwise, these will be at 0, nothing will happen. So I have to have my clock, falling edge, and I have to have Q0 as 1 and Q1 as 1 to get my output to change for Q2. So that's how I'm going to create my up counter. Now, how would I create a 4-bit up counter? Hopefully you can see that what I would need to do is add another flip-flop. I would add another flip-flop here. I've got JK, my clock, again falling edge clock. I'd have Q3 and Q3 not. So for this one, I would be tied in again to my clock because they're synchronous. But J and K would be connected with an AND gate as well, because I'll put it over here. But as you can imagine, I'm going to have 3 conditions. My 3 conditions being that Q0 is going to be equal to 1, Q2 is going to be equal to 1. Sorry, I didn't get Q1. Q1 is, or sorry, Q0, I'm going to need Q0. Did I get that one? I got Q0. I need Q1, which is right here. And I need Q2. So a little confusing on that one. That would give me Q3 as my 4th bit. So for an up counter, simultaneously clocked, the condition is that the previous outputs are also at 1. So when I connect those to J and K, it allows my clock to toggle only on those conditions. So that's your synchronous counter up counting SSI counter.